Inside a generation ship, a technician replaces a worn valve in one of the water lines. The spare part is already beside him, packed on Earth long before he was born, and carried for the day this repair would eventually be needed. Nothing unusual has happened. The work is routine, and that is exactly what the ship's builders intended. They knew the voyage would continue after they were gone, so they designed the ship for people who would inherit the mission rather than choose it. We usually imagine that this is the hardest part of a generation ship, keeping the ship working, raising new generations and carrying a human society safely across the centuries. If all of that can be done, then leaving first seems like an enormous advantage. But Earth would not stop changing after the launch. While the first ship continues between the stars, researchers at home could develop faster engines and more reliable life support systems. A second ship, launched decades or even centuries later, might complete the same journey in far less time, even though it left Earth long after the first. The original crew could do everything right. Their descendants could maintain the ship, preserve its knowledge and keep the mission on course. Then, one day, a message from Earth might tell them that another vessel has launched behind them and is expected to arrive first. The original ship would still be working, and the crossing could still be going exactly as planned. Yet the mission might no longer be the one its builders imagined. Being overtaken would change more than the arrival date. The first ship may have organized its society around founding the first settlement. Its laws and training may assume that no one will be waiting at the destination, but a later ship could arrive with better equipment, newer instructions, and its own idea of how the colony should be governed. So the real question is not simply whether the first generation ship can survive the crossing. It is whether it can survive for centuries without being made obsolete by the civilization it left behind. By the end of this video, you will understand how a later ship could overtake the first, why a generation ship built to last may also be difficult to modernize, and what both crews would face if the newer mission reached the destination first. If you enjoy exploring questions like this with me, subscribing helps others find them too. Liking and sharing the video helps even more. Now, let's begin. This part seems simple at first. One ship leaves Earth, and a faster ship leaves later, so the faster ship catches it. But the word later carries most of the problem, because every year spent waiting gives the first ship more distance that must be recovered. Speed alone doesn't tell you who arrives first. Take a worked example, using made-up speeds so we can see the geometry without pretending they describe a real spacecraft. Suppose the first ship covers 1 light-year per century. By the end of 50 years, it is half a light-year from Earth. The second ship now launches and travels twice as fast, covering 2 light-years per century. Yet it gains on the first ship at only 1 light-year per century, so closing the existing gap still takes 50 years. You can hold the whole calculation in one image. 2 marks sliding along the same ruler. The second mark moves twice as fast, yet the space between them closes much more slowly than you might expect. Its full speed does not erase the lead, only the difference between the 2 speeds does that work. That difference is called the closing speed, and here it is much smaller than the second ship's speed as measured from Earth. From Earth, the meeting happens 100 years after the first launch. By then, both ships are 1 light-year away. The first ship has spent a century traveling, while the second has spent 50 years traveling. Faster helped, but the 50-year delay consumed a large share of the advantage before the second ship even moved. If their destination were closer than 1 light-year, the first ship would already have arrived. Change the delay, and the result changes with it. If the second ship leaves after 10 years instead of 50, the first ship is only 1/10 of a light-year ahead. At the same pair of made-up speeds, the catch takes 10 more years. Waiting less doesn't make the newer engine any faster. It simply leaves less distance for that engine to recover. This example also shows where our confidence ends. We can calculate an overtake once we choose departure times and steady speeds. But those choices are assumptions, not forecasts. Real missions would include acceleration, braking, equipment limits, and a destination that might be reached before any meeting is possible. A ship that arrives first cannot be overtaken along the way. So the launch decision cannot rest on the hope that better technology will appear someday. It needs a threshold based on both speed and delay. How much faster must the later ship be, and how soon must it leave before waiting truly wins? This part of the problem looks simpler at first than it really is. Proxima Centauri is the closest star to our Sun, and NASA gives its distance as just over 4 light-years. That makes it a good place to test the waiting problem, because the destination is fixed and the race has a finish line. Take 2 ships and keep the arithmetic gentle. These are example speeds, not predictions about engines we know how to build. The first ship leaves for Proxima at 1/10 the speed of light. At that steady speed, and ignoring the time needed to accelerate and brake, the trip takes a little more than 42 years. Its passengers settle in for a voyage that will consume much of a human life. Now suppose Earth waits 20 years before launching a second ship at twice that speed, 2/10 of light speed. By then, the first ship has travelled about 2 light-years. It has crossed nearly half the distance to Proxima, so the later crew begins with what looks like a crushing disadvantage. But the closing speed is 1/10 of light speed. The second ship gains 1 light-year every 10 years, which means it catches the first after another 20 years. At the meeting, both ships are about 4 light-years from Earth, very close to Proxima, but not quite there. The newer ship then reaches the star first, roughly 1 year ahead of the vessel that left 2 decades earlier. That is the durable image, 2 ships meeting near the end of the road, with the younger one carrying people who stayed on Earth long enough to watch the first crew disappear from public memory. The first launch was not pointless. It proved that the voyage could begin. Yet in this worked example, its passengers spent decades travelling only to see a later machine slide past them within sight of the destination. The result changes if we move any of the assumptions. A slightly slower second ship may catch the first after Proxima, which means there is no overtake during the mission. A longer delay can erase the gain completely. Acceleration, braking, fuel, radiation shielding, and failures would also change the outcome, and no current program can tell us when either example speed will become practical for a crewed starship. So the decision is not simply whether tomorrow's ship might be faster. It is whether a plausible gain can overcome the first ship's lead before the destination ends the race. How large must that gain be before keeping everyone on Earth becomes the safer choice? This part looks simpler at first, because 2 ships passing each other seems like a single event. On a chart, one line crosses another. The crews wave through 2 layers of shielding, and the faster ship moves ahead. But a launch decision can't rest on the crossing alone. The second ship also leaves Earth later, so its crew spends years waiting before their voyage even begins. Take a pair of cups sliding across a long table. The first cup starts now and moves 1 handspan each second. 5 seconds later, the second cup begins moving 2 handspans each second. It needs 5 more seconds to draw level, because each second of travel closes only 1 handspan of the lead. By the time they meet, 10 seconds have passed since the first cup moved. That small example carries an awkward result. The second crew reaches the meeting point after 5 years in flight, while the first crew has already spent 10 years travelling. Yet the people assigned to the second ship also waited 5 years on Earth. Measured from the first departure, both groups have given up the same 10 years before the overtake. The faster ride has not returned those waiting years. It has merely placed them before launch. This is the second wake, the stretch of human time behind the later ship. A mission planner has to count it along with flight time, because the destination does not care where the years were spent. If the second ship waits too long for better engines, even a much higher speed may produce only a modest improvement in arrival. If it launches soon enough, the gain can be large. The crossing point tells us which case we have. The example is only geometry. It does not show that either speed can be built, and it says nothing about how long a real crew could remain healthy while waiting or travelling. Real missions would also carry different crews, ages, and medical limits. It also leaves out acceleration and braking, which would round off those clean lines and usually push the meeting farther away. Without a tested propulsion system, Any chosen speed is an assumption, not a forecast. Still, the decision has changed. We are no longer comparing one travel time with another. We are comparing complete lives, years aboard the first ship, years spent on Earth awaiting the second, and the remaining years after arrival. A later launch may win the race, while offering its passengers very little extra lifetime at the destination. So whose clock should decide when the second ship is worth waiting for? Voyager 1 offers a tempting baseline because it is already leaving the solar system. Treat its measured speed as a model for the first trip to another star, extend the line, and you can see how long the crossing lasts. NASA's tracking data puts Voyager 1's speed relative to the Sun at about 38,000 miles per hour, roughly 17 kilometers per second. That is fast enough to cross the continental United States in under 6 minutes. Yet on a chart of nearby stars, its yearly progress would barely show. The spacecraft covers about 3.5 times the distance from Earth to the Sun each year, while the nearest star system sits more than 260,000 times that Earth-Sun distance away. You can make the scale visible with a long strip of paper. Mark the Sun at one end, then place Earth about the width of a pencil line away. On that same scale, Proxima Centauri would not fit across your desk or even across the room. You would need to carry the paper outside and keep walking. Voyager's speed is impressive near planets because our planetary neighborhood is tiny compared with the space between stars. If Voyager 1 happened to be aimed at Proxima Centauri, which it is not, dividing the distance by its present speed gives a travel time of roughly 75,000 years. That is an estimate, not a mission forecast. It treats the spacecraft as though it could hold the same course and speed for the entire crossing, and it ignores the problem of slowing down when it arrived. Voyager also carries no repair shop, food system, shielding for thousands of generations, or engine able to change its fate after launch. Its radio signal weakens as the distance grows, and NASA expects its scientific instruments to shut down one by one as its plutonium power supply fades. The craft may continue drifting long after it can no longer speak to Earth, but silent survival is a very different achievement from delivering living passengers. So Voyager gives us a baseline by showing how little even a record-setting spacecraft accomplishes against interstellar distance. It does not tell us how a starship would work. It tells us how much faster, tougher, and more self-contained that ship would have to be before departure could be justified. If coasting like Voyager leaves us tens of thousands of years from arrival, what kind of engine could bring that crossing inside a human lifetime? A star chart can make the distance between suns look like a line you could cross with enough fuel. But a line on paper has no clocks, mules, broken pumps, or children growing older before the ship reaches the other end. NASA measures Voyager 1 moving away from the Sun at about 17 kilometers per second, or roughly 38,000 miles per hour. At that speed, crossing just one light year would take about 17,600 years. A light year is the distance light covers in 1 year, about 9.5 trillion kilometers or 5.9 trillion miles. The nearest stars are several light years away, so even the smallest useful mark on a stellar map can contain more time than all of recorded human history. That changes what the crew is asking the engine to do. Speed is no longer just about arriving sooner. It decides how many generations must live aboard, how long every seal and cable must last, and whether the people who choose to leave could ever expect to see the destination. A trip lasting 80 years is a hard voyage. A trip lasting 800 years becomes a moving society whose first passengers will never meet the people who arrive. The durable image is a ship's maintenance calendar stretched across centuries, from launch through final arrival. On Earth, a worn pump can be replaced by another pump made in another factory. Between stars, there is no factory waiting nearby unless the ship carries one. Each added decade means more spare material, more power, and more chances for a small failure to meet another small failure. It also means the ship must support births, deaths, training, and decisions made by people who never agreed to the launch. We can calculate travel time from a chosen speed, But that calculation cannot tell us whether a closed human community would remain healthy and capable for centuries. No mission has tested that. Space stations have taught NASA and its partners how people and machines behave through months and years in orbit. Yet an interstellar crossing would extend the test far beyond any direct evidence we have. So distance turns into time, and time turns into mass, maintenance, and human continuity. Making the ship faster could reduce every one of those burdens, but gaining speed demands energy, while slowing down at the far end demands still more. How fast would the ship need to travel before its crossing stopped being a civilization project and became a voyage one crew could finish? A faster ship sounds like the clean way out, until you look at what the ship must carry. It cannot be a cabin wrapped around an engine. For a voyage lasting longer than one human life, it has to provide air, water, food, heat, medical care, spare parts, and enough living space for people who never agreed to leave Earth because they were born after it vanished from view. A sealed greenhouse gives us a small version of the problem. Plants take in carbon dioxide and release oxygen, while people do roughly the reverse. Water can be cleaned and used again. Waste can feed crops. On paper, the loops fit together. In a real habitat, crops get sick, filters clog, chemicals collect where nobody expected them, and every repair draws from a supply that cannot be replaced from home. The International Space Station has shown how demanding even partial recycling can be. NASA says its water recovery systems reclaim about 90% of the water used on board. That is a remarkable achievement, but the station still receives equipment, food, and replacement parts from Earth. Its crew can also come home. A Starship would have no cargo launch arriving next month, and no hospital waiting a few hours below. Now stretch that problem across generations. The ship needs more than machines that last. It needs people who can inspect them, understand them, and teach someone younger how to rebuild them. A pump may be replaced by a spare, but after several replacements, the crew must be able to make the seal, shape the metal, test the new part, and know why the old one failed. The workshop begins to matter as much as the engine. That changes the vehicle itself. More people may protect the community from illness, accidents, and a dangerously narrow gene pool. Yet every added person needs food, water, room, and protection from radiation. More farmland means more lamps or more sunlight collected outside. More shielding means more mass. More mass demands more energy to accelerate, and again to slow down. No existing spacecraft has proved that a human community can keep all these systems working for centuries. The station, Antarctic research bases, submarines, and closed habitat trials each test pieces of the problem, never the whole crossing. So the first interstellar ship cannot be treated as transport alone. It would be a small moving world, launched before anyone could know whether its society would work as well as its machinery. What kind of community could survive inside it? A launch date can look like a simple square on a calendar, but for the people approving an interstellar mission, that square carries a peculiar risk. Authorize the ship now, and a faster design developed later might pass it before it reaches the destination. You can see the problem in a pair of departure permits sitting on the same desk. One permits a proven ship to leave soon. The other delays the mission in hope of better engines, lighter shielding, or a more efficient power source. Waiting could shorten the total time until anyone arrives. It could also become a habit with no natural stopping point, because there will nearly always be another promising design just beyond the current budget cycle. The mathematical version is often called the weight calculation. In work published through the British Interplanetary Society, Andrew Kennedy examined how improving travel speed could create a best time to depart. The logic is much like waiting for an express train instead of boarding the local train already at the platform. If the express arrives soon enough and travels fast enough, waiting gets you there first. But the calculation depends on a rate of progress that no one can guarantee. Computer chips followed a strong historical trend for decades. Interstellar propulsion has no comparable record of completed voyages. We have laboratory results, engineering studies, and spacecraft that have crossed our own planetary system, but no long series of Starship generations from which to draw a dependable curve. Extending any recent trend across decades or centuries turns a measurement into an assumption. That changes the burden on the launch decision. The first ship should not be delayed merely because later ships may improve. Delay is justified only when a specific advance has credible tests, a believable development path, and enough expected benefit to outweigh the years spent on Earth. A reactor demonstrated in hardware deserves more weight than an engine that works only in equations, however attractive those equations may be. The incentive trap appears when every committee is rewarded for avoiding the visible failure of an early launch, while nobody is clearly responsible for the invisible cost of waiting. A ship that departs and struggles leaves records, names, and blame. A ship postponed for another review leaves no wreckage. It also makes no progress. So the launch window cannot be chosen by optimism alone, or by fear of being overtaken. It needs a rule that can tell a genuine breakthrough from another reason to remain at the platform. What evidence would be strong enough to let the first ship leave? This part of the problem looks simpler at first than it really is. If a better engine may arrive soon, waiting can seem like the careful choice. But a launch date sits on a calendar beside aging hardware, trained crews, stored fuel, political support, and people whose working lives don't pause while the propulsion team tries to gain another fraction of speed. A useful object to keep in mind is the ship's departure ledger. On one side, engineers record what a delay might buy: a tested engine, lower fuel demand, stronger shielding, or a shorter trip. On the other side, they record what the same delay costs. Components must be inspected again, suppliers may close, specialists retire or move on, designs change, and each change can force another round of testing through systems that were already approved. The strange part is that progress can make the first ship harder to launch. A new engine may perform better on a test stand, yet fitting it into the vessel could alter the power system, cooling pipes, fuel tanks, and balance of the whole craft. Replacing one machine can become a redesign of everything touching it. The ship gains a faster engine on paper while losing another stretch of time at the platform. There is also a limit to what current evidence can tell us. A laboratory test can show that a component works under controlled conditions. It cannot prove that the same component will survive decades of vibration, radiation, dust, repairs, and imperfect maintenance. Longer testing reduces some risks, but the test program itself can never reproduce the entire voyage. At some point, waiting stops buying certainty and starts buying a different set of unknowns. So the departure rule needs two thresholds, not one. The new technology must offer enough improvement to justify reopening finished work, and the evidence behind that improvement must be strong enough to survive contact with the rest of the ship. A small gain that forces a large redesign may push launch farther away. A modest, well-tested system that fits the vessel may carry people toward another star sooner. That doesn't mean speed should be dismissed. A major propulsion advance could allow a later ship to catch an earlier one, which would be a grim reward for the first crew's courage. But avoiding that possibility at any cost creates its own trap. Every proposed ship can be held for the next machine, then the next. If both launching and waiting can waste years, who decides when an improvement is large enough to stop the clock? This part of the problem looks simpler at first than it really is. A launch date seems like a square on a calendar. Choose one, finish the ship and go. But the date is also a bet on the shape of technological progress, and that shape can't be read in advance. A useful object to keep in mind is the propulsion system sitting on a test stand. Engineers can measure what it does today, how often it fails, how much waste heat it produces, and whether its parts can be repaired. Beside it sits a proposed replacement that may be faster, lighter, or more efficient. On paper, waiting looks sensible. The replacement promises more distance for the same fuel or the same distance in less time. The trouble is that a promise doesn't travel. A working engine does. Each new design brings a fresh chain of tests, factories, spare parts, control systems, and failure modes. Even if its central idea succeeds, fitting it into the ship may expose problems that weren't visible on the test stand. The launch date then moves once for the better engine, and again for everything the better engine changed. Those extra years count as part of its performance too. Waiting only pays when the gain arrived soon enough and is large enough to recover the lost time. You can think of two lines drawn across a sheet of paper. One line belongs to the ship we can build now, moving steadily away from Earth. The other begins later but rises more sharply because the newer ship is faster. If the second line crosses the first before the destination, waiting may bring humanity there sooner. If the lines never cross, the delay brought better machinery but a later arrival. That drawing is memorable because it also shows the limit of the argument. We don't know the future line. Progress can move quickly for a while, stall on a stubborn material problem, or produce gains that work in a laboratory, but not inside a vessel expected to run for generations. Past trends can help set a range, but they can't supply the missing curve. So the launch decision has to use evidence that exists at the time: demonstrated performance, integration risk, likely development delay, and the size of the gain required to catch the ship already underway. That won't remove uncertainty. It does stop hope from being treated as a schedule. And once the faster design wins on paper, what proof should it have to provide before everyone on Earth agrees to wait? This part looks simpler at first because both designs have a clear object at the center. Daedalus carries a large robotic probe. Starshot carries a tiny chip behind a bright sail. Make the probe smaller, push it faster, and the waiting time falls. Yet the two designs reach for speed in very different ways, and each one moves the burden somewhere else. Between 1973 and 1978, a team from the British Interplanetary Society developed Project Daedalus as a design study. Their uncrewed probe would burn frozen pellets of deuterium mixed with helium-3, striking them with electron beams to trigger tiny fusion explosions. Magnetic fields behind the engine would direct the hot material backward. You can think of it as throwing pebbles from a cart to make the cart roll the other way, except the pebbles become fusion plasma and must be fired hundreds of times each second. The study calculated that Daedalus might reach about 12% of light speed during a flyby mission to Barnard's star. That was a result on paper, not an engine anyone had built. The probe would have needed tens of thousands of metric tons of propellant, including helium-3 gathered from Jupiter's atmosphere. No one has demonstrated the required fusion drive, the pellet system, or the vast fuel operation around Jupiter. Daedalus showed that known physics could describe a fast probe while leaving a very large stack of machines still to be invented. Breakthrough Starshot shifts the burden. Announced in 2016, the privately funded research program proposed sending gram-scale craft toward Alpha Centauri at roughly 20% of light speed. Instead of carrying fuel, each craft would ride a thin reflective sail pushed by powerful lasers on Earth. It resembles a leaf driven across a table by a fan, except we replace the fan with a laser array and expect the leaf to survive acceleration thousands of times stronger than gravity. At the proposed speed, the trip could take a little over 20 years. Again, that figure belongs to a concept, not a completed flight system. The sail must stay light, reflective and stable under an intense beam. The lasers must act as one enormous instrument. Then a chip-sized probe has to survive dust impacts, take useful measurements, and send its data across more than 4 light-years with very little power. The image is simple. Daedalus is a mountain of fuel pushing one heavy probe, while Starshot is a field of lasers pushing something closer to a postage stamp. Both shorten the voyage by making another part of the mission extremely difficult. So which burden can we reduce first? The mountain, the laser field, or the fragile craft at the far end? A probe can be built around the trip, while a habitat has to be built around the people inside it. That difference sounds small until you look at the chair where someone would spend the voyage. A chip can tolerate hard acceleration, deep cold, and long periods without repair. A passenger needs air, water, food, warmth, sleep, and enough room to remain healthy. The people must still be alive and well when the engines finally stop. Speed changes when all of that comes aboard. The sail concept we just met depends on keeping the craft extremely light. because the same push produces less acceleration as mass rises. It's like trying to move a shopping cart with a desk fan. An empty cart may roll, fill it with water tanks, shielding, spare parts, and several people, and the fan hasn't become weaker. It simply has much more to move. Even the systems that recycle air and water need pipes, pumps, power, backup parts, and protection from failure. A human ship also can't treat a rival as a probe does. A fast probe may pass its target, gather what it can, and send the results home. A habitat carrying people must usually slow down and enter a safe path around a planet or star. That means bringing another way to remove nearly all the speed gained during departure, or arranging some braking system at the destination. Fuel carried for braking adds weight during the entire outward trip. The faster the cruise, the larger that arrival problem becomes. Then there is the material between stars. Interstellar space is sparse, but it isn't empty. At a high fraction of light speed, a grain of dust meets the ship with far more energy than its size suggests. A tiny probe might accept that risk through numbers, sending many craft in the hope that enough survive. A crude habitat can't use people as replaceable copies, so protection adds mass, and added mass asks for more energy at departure and more braking at arrival. None of this shows that a fast habitat is impossible. It shows where the evidence stops. Probe studies can test propulsion ideas, beam control, sails, electronics, and communication without proving that the same approach scales to a living ship. They can tell us whether a very small craft may cross the distance. They cannot yet tell us the mass of a safe home, how its systems would last, or how its crew would arrive slowly enough to stay. The image to keep is a postage stamp beside a sealed house. Both may cross the same distance, but only one must carry a working world. So before speed becomes useful for people, how much ship must we carry just to keep the passengers alive? This part of the problem looks simpler at first than it really is. Once a probe can survive the trip, launching it as soon as possible seems like the safe choice. Yet the launch date and the travel speed are tied together, and improving one can make the other look badly timed. Think of two trains leaving the same station for a very distant town. The first train leaves tonight and crawls the whole way. A much faster train leaves years later, passes it somewhere along the track, and arrives first. The early passengers have spent longer travelling only to watch the later train disappear ahead of them. Interstellar probes can face the same awkward result. A craft launched with the best system available at the time might still be overtaken by a later craft built after propulsion, materials, or beam control improved. Researchers sometimes call this the incentive to wait, but it isn't a law telling us when to launch. It's a decision problem built from assumptions about how quickly technology will improve, and those assumptions can fail. The object worth remembering is the first probe's radio. Long after launch, it receives news from Earth that a faster successor is being prepared. Nothing has gone wrong with the first craft. Its engine works, its instruments remain alive, and it keeps moving toward the target. Even so, the mission planners now know that the newer probe may reach the star earlier and carry better instruments when it gets there. That asymmetry changes the burden of proof. Waiting has a possible benefit because the next craft may be faster, but it also has a certain cost. No mission leaves during the delay. Launching has the reversed shape. We gain real flight data and begin crossing the distance, while accepting the chance that later engineering will make the craft look slow. No concept study can settle that trade by itself. A paper can compare assumed launch dates, speeds, and rates of improvement, but those inputs are not a schedule for future inventions. We don't know whether progress will arrive steadily, stall for decades, or solve one part of the trip while leaving another untouched. For a small scientific probe, being overtaken may be tolerable. The first craft could still test hardware, measure the space between stars, and teach the builders of its successor. For a crewed ship, the choice is harsher. People cannot be recalled, upgraded, or transferred easily when a better vessel leaves home behind them. So the first launch needs more than a speed that works on paper. It needs a reason to leave now, despite what the next generation may build. What evidence would make that decision justified? A habitat can look like a room on a drawing, with walls, lights, storage, and enough space for people to move around. But the room is the easy part. A real habitat also carries the machinery that makes the room livable, along with replacements for that machinery when it stops working far from Earth. The International Space Station gives us the clearest working example. NASA's operating record shows a place kept alive by linked systems that manage air, water, temperature, power, waste, and fire risk. Those systems need filters, pumps, valves, sensors, cables, seals, and tools. They also receive regular cargo from Earth, while flight controllers and engineers on the ground help crews find faults and plan repairs. An interstellar habitat would lose both forms of support. So the concrete object to keep in mind isn't the outer hull, it's a spare pump sitting on a shelf. That pump has mass, so does its replacement, and perhaps the replacement for that replacement. If the pump depends on a control board, a special lubricant, or a seal made from a material the ship cannot produce, each dependency adds another item that must survive the whole trip. You can reduce that burden by carrying machines that make parts, but those machines bring their own tools, feedstocks, power demands, and failure points. A workshop helps, though it never turns repair into magic. It also needs people who remember how to use it after years when nothing similar has broken. Redundancy has the same stubborn shape. 2 air scrubbers may protect the crew if one fails, unless both share a weak component or were damaged by the same event. Engineers call that a common mode failure. The backups exist, but one cause can defeat them together. The safer answer may be different designs placed in separate sections of the ship. That protects life better, while adding pipes, wiring, shielding, inspection work, and more mass. We can learn from submarines, polar stations, and spacecraft, but none of them proves that a closed habitat can support generations without outside supply. Their records reveal real failure modes and repair habits. They do not give us a completed interstellar design, because every one of those places still belongs to a support network. Even the best isolated station can expect a shipment, an evacuation, or advice from specialists elsewhere. This changes what counts as launch ready. A ship cannot merely carry enough equipment for its systems to work on departure day. It must carry a repair economy, stored parts, raw material, manufacturing tools, test equipment, and people who can preserve skills that may not be needed for decades. Some failures can be planned for. Others will appear only after materials have aged together in a closed environment longer than any habitat has yet operated. How much of a world must the ship carry, and how much can its people rebuild along the way? A backup seems to settle the problem until engineers ask what keeps that backup working. Give every vital system a second unit, then give that unit its own spare parts. But a spare water pump is not just a pump sitting on a shelf. It also needs seals that will not crack during storage, clean lubricant, compatible pipes, electrical controls, tools for opening it, and some way to prove that the repair worked. A second pump adds mass, and that extra mass spreads through the ship. The structure must hold it during acceleration. The engines must push it. More propellant may be needed to move the larger vehicle, which can require larger tanks and more structure around those tanks. Engineers call this a mass cascade. One added object creates several less visible additions before the design closes. A backpack gives you the smaller version. Add a heavy bottle, and you may need a stronger pack with wider straps. The stronger pack weighs more too, so the burden on your shoulders grows by more than the bottle alone. On a starship, the same effect reaches into propulsion, cooling, power, shielding, and the machinery used to move supplies through the habitat. Redundancy makes the cascade harder because identical backups can share the same weakness. 2 pumps from one production run may contain the same flawed seal. 2 computers running the same software can fail after the same error. Real protection may require different designs, separate power paths, physical distance between units, and repair methods that do not depend on one tool or one trained person. Each layer buys safety while adding more material to inspect, maintain, and eventually replace. Even placement carries a cost. Separating 2 backups protects them from one fire or impact, But now the ship may need longer pipes, extra wiring, more valves, and access routes to both locations. We do not yet have a measured figure for the full penalty on a self-supporting starship. No institution has operated a closed human habitat for the centuries needed to reveal every slow failure, so any exact total would come from design assumptions rather than a completed test. What we can say is narrower. Reliability cannot be priced by counting duplicate machines alone. The ship must also carry the hidden support behind them. That changes a launch decision. Removing a backup makes the vehicle lighter, but it may leave one brake capable of ending the mission. Adding another can make the ship safer, yet the added engines, fuel, structure, cooling, and maintenance work may create fresh ways to fail. The design team is not choosing between safety and recklessness. It is choosing which failures the ship can survive without making the ship too large to build and launch. So the lasting image is not a warehouse full of spare boxes. It is one spare pump casting a long shadow across the whole vehicle. How far can that shadow spread before added protection stops making the ship safer? This part of the problem looks simpler at first than it really is. Once engineers have chosen enough backups, you might expect them to add up the mass, close the design, and start building safely. But a ship this large would take years to assemble, and knowledge would keep moving while the hardware waited its turn. A good object to hold in mind is a sealed cargo pallet sitting beside the launch site. Inside it is a control unit designed early in the project. By the time that pallet is ready to fly, a newer unit may be lighter, use less power, and survive heat better. Replacing the old one sounds sensible. The trouble is that the new unit may need different cables, software, cooling, tools, and spare parts. One improvement can reach into half the ship. That creates a slow kind of freight. Progress itself has to be carried through the design. Every change must be checked against equipment that was chosen before it, including equipment already built and perhaps already launched. If the team accepts every better component, assembly may never settle. If it freezes the design too early, the first ship can leave with systems that were dated long before departure. Space programs already manage this problem by qualifying hardware for a specific environment and controlling changes after a design is approved. That practice shows what can be tested here on Earth. It doesn't prove that any chosen system will remain repairable across an interstellar voyage. The boundary is important because long life adds a demand that launch hardware rarely faces. The ship must preserve not only machines, but the ability to understand, remake, and adapt them. So the pallet may need more than a replacement control unit. It may need its test equipment, manufacturing files, compatible materials, and enough knowledge for someone far removed from the original engineers to diagnose a failure. Carrying a finished part solves one expected problem. Carrying the means to produce parts can answer many problems, but the workshop has its own mass, power draw, waste heat, failure points, and need for skilled people. This doesn't mean newer technology always makes the ship heavier. Better materials and more efficient electronics could remove mass. We can't know the balance before the actual design, because every saved pound may alter several connected systems, while every new capability brings support equipment of its own. The unresolved edge sits between those two effects. The lasting image, then, is that sealed pallet waiting beside the launch site while the world around it keeps learning. At some point, the engineers must stop improving it, certify what they have, and trust that the ship can carry enough knowledge to improve itself later. But where should they draw that line? Crew size can look like a seating problem. Count the bunks, fill them, and leave a few empty for emergencies. But on a ship that may travel for generations, a bunk is also a place in the family tree, and that changes what enough people means. The durable image is a wall of name cards in the ship's medical office. Each card records a person's age, health, skills, and family connections. Before a child is conceived, the crew may need to check that wall, because a small population can lose genetic variety as relatives become more closely connected over time. A run of deaths, infertility, or births tilted toward one sex could narrow the choices further. The ship might still have plenty of food and empty beds, while its future population is becoming harder to sustain. Published crew estimates don't give us one settled minimum. They come from computer models, and each result belongs to the assumptions inside that model. How long the voyage lasts, how many founders begin it, how reproduction is managed, what accidents occur, and whether stored sperm, eggs, or embryos are available. Change those inputs and the number changes. So a quoted minimum is not a law of nature. It is the smallest population that survived one designed set of risks. That source boundary has a practical consequence. Engineers cannot choose the crew count first and treat everything else as fixed. A larger founding group improves the odds that rare genes and vital skills won't vanish after one bad generation. But every added person needs decades of food, water processing, living space, medical care, and heat removal. A smaller group makes the ship lighter, yet asks reproductive planning and stored genetic material to carry more of the risk. And people are not interchangeable samples. A planned pairing may be refused, a pregnancy may fail, or a child may not want the profession the ship needs. These possibilities are part of family life, and even perfect records cannot turn them into a maintenance schedule without placing a heavy burden on the people living inside it. The awkward part is built into the design. Preserving freedom may require more spare capacity than a strict survival model allows. We can test possible populations in simulations, but we have never watched a closed human community reproduce through centuries of deep space travel. The models help expose weak assumptions. They cannot certify a crew against every disease, accident, choice, or change in behavior. That leaves the launch decision resting on a margin no equation can fully prove. So how much extra room, food, and genetic variety should the ship carry before its crew minimum becomes a population with a fair chance to remain human? A ship can keep everyone alive and still become a place no one would choose to live. You might see the problem at the dining table, where meals are shared by people whose work and future were set long before they had any say. Survival asks whether the crew has food, water, medical care, and enough genetic variety to continue. Flourishing asks for something harder to build into a ship, the freedom to refuse. A person should be able to leave a job or say no to a relationship. A child should have some chance to become someone the planners never expected. That freedom changes the design. Suppose only one crew member knows how to repair the carbon scrubber. On paper, that person can choose another kind of work. In practice, everyone needs them to stay where they are. A second trained worker gives both people room to choose. But training takes time, and the machines must be made so more than one kind of person can maintain them. Redundancy, then, isn't limited to spare equipment. The ship also needs spare human capacity, so an illness, a conflict, or a change of heart doesn't turn a skill into a life sentence. Studies of Antarctic stations and long space missions can tell us something about life in close quarters. They show that little privacy and fixed roles can strain mental health and relationships. But those studies stop well short of a true generation ship. Their crews know they can return home. Outside help remains available to them, and their missions last months or years, not centuries. The evidence shows where pressure may begin, but it cannot tell us what happens when nobody has an exit. So the launch plan must make room for things that don't clean the air or grow food. People need some privacy and some time that belongs to them. They also need spaces that can change as later generations find new uses for them. At an engineer's desk, this may look like wasted mass. Inside the ship, it could keep each friendship or career from becoming another part of the maintenance system. More people would offer a wider choice of partners and skills, but crew size cannot guarantee consent, fairness, or trust. Those depend on rules and customs that later generations can change, even when the first planners believed they had solved the problem. The ship must arrive with living people, but it must also carry enough freedom for them to build a society that Earth never scheduled. How much launch mass should be set aside for lives that cannot be planned in advance? A ship's rulebook may look like the lightest thing aboard, perhaps a few files stored in several computers. Yet those files could control who may have children, who gets trained to repair the reactor, and who must surrender a cabin when space becomes scarce. Some rules would be needed before launch. A small, closed population cannot leave every berth, medical duty or dangerous job to chance. If too many people enter the same age group, the ship may later face a shortage of experienced workers, followed by a shortage of caregivers. If essential knowledge stays within one family, a single accident could take that knowledge with it. The crew would need ways to spread skills and plan for needs that arrive decades later. But a rule built to solve one risk can create another. Suppose the founders give a council the power to approve pregnancies because the farms and living quarters have fixed limits. That decision may help balance food, labor, and age. It also gives a small group authority over the most private choice a person can make. The council's children would inherit that system without ever agreeing to it. This is where the rule book becomes heavy. It is carrying decisions across generations. Evidence from isolated communities on Earth can show how people share scarce supplies, divide work, and respond when authority fails. Historical records can also show that rigid systems often outlive the conditions that first produced them. Neither source can tell us exactly how people born between stars would behave. No human community has remained sealed inside a spacecraft for centuries, with no larger society to trade with, leave for, or ask for help. So a credible design would need more than rules. It would need a lawful way to change them. That might mean written rights that a temporary majority cannot remove, regular reviews of emergency powers, and more than one route for resolving disputes. Even those protections carry risk. A system that is too easy to change may fail during a shortage, while one that is too difficult to change may turn the founders' fears into permanent law. You can make the problem visible with one object, a sealed copy of the ship's founding charter, placed beside a procedure for amending it. One document says what the first crew feared, the other admits that their descendants may know better. The first ship would therefore launch with two social duties that pull against each other. It must protect a population from choices that could end the mission, while protecting people from a mission that claims too much power over their lives. Who gets to decide when survival is serious enough to close that second protection? A sealed tank of green algae can look like the easy part of a generation ship. Give it light, pipe in carbon dioxide, collect oxygen, and the living machine seems ready to run. The difficulty begins when that tank has to work beside every other part of the ship for years without soil, a river, or a fresh delivery from Earth. The European Space Agency has spent decades testing that larger idea through MELISA, short for Microecological Life Support System Alternative. ESA describes it as a closed-loop system, modelled on the way aquatic ecosystems recover useful material from waste. Instead of treating used water, carbon dioxide, and organic waste as things to store or discard, MELISA divides the work among linked biological compartments. You can remember it as a row of connected vessels. In one, microbes break waste into simpler material. Other microbes change those products into forms that plants and algae can use. A final compartment grows food plants, while algae help produce oxygen and edible biomass. Water and nutrients move around the loop, but each vessel depends on the others sending the right material at the right rate. That dependence is both the evidence and the warning. At the MELISA pilot plant, run by the Autonomous University of Barcelona, researchers have built and tested parts of this loop under controlled conditions. ESA reports experiments linking several compartments, including tests in which rats consumed oxygen while algae restored it. Those trials show that biological recycling can perform real life support work. They don't show that a complete human settlement can seal the hatch and remain independent for generations. A ship would also need to handle the less cooperative parts of biology. Microbes mutate. Plant harvests vary. Pipes gather films of living material. A treatment that removes one unwanted organism may harm another compartment the crew needs. Even a healthy system changes as people eat different meals, become ill, have children, or adjust the amount of food they grow. The equipment must detect those shifts before a small mismatch passes through the whole loop. MELISA moves the first ship closer to launch in one sense. It replaces a hopeful sketch with working hardware, measured flows and failures that engineers can study. But it also reveals how much control a closed ecology demands. The crew won't merely tend plants, they'll manage a web of organisms whose waste, air, water and food are tied together, with no outside ecosystem waiting to absorb a mistake. So when that row of vessels drifts out of balance, how much time will the crew have to put it right? A living loop can recover from small changes, but it still depends on manufactured parts. Take a circulation pump. It may sit beneath a tank, moving water past roots and microbes day after day, so steadily that nobody gives it much thought. Yet the organisms in that tank depend on the flow it creates. If the pump slows, oxygen levels can change, waste can collect, and a healthy biological process can become a repair job. That makes the ecology look less like a garden and more like a factory whose machines happen to be alive. Every part has an input, an output, and a rate it can handle. Plants need light, water, carbon dioxide, and nutrients in workable amounts. Microbes need the right conditions to turn waste into forms the plants can use. Pumps, valves, sensors, pipes, and control software keep those exchanges moving. The crew may see green leaves, but behind them is an industrial system with tolerances. A vegetable bed offers a simple image for this burden. On Earth, soil hides a great deal of work. It stores nutrients, holds water, contains countless organisms, and gives roots room to spread. A ship cannot count on deep soil or a wider environment to soften every mistake. Its growing beds must perform those jobs within a limited mass and volume, while remaining clean enough to inspect and repair. That last part is easy to overlook. Food production cannot stop while the crew dismantles a clogged pipe or waits for a replacement sensor. Living components also refuse to follow a maintenance calendar. A crop may be halfway through its growth when a lamp fails. A microbial tank may need stable conditions while another part of the loop is being cleaned. Repairs must happen around biology that continues eating, breathing, growing, and producing waste. So the ship needs spare capacity, replacement parts, and ways to isolate trouble without shutting down the whole loop. Those protections add mass and power demand, and they require crew time. We do not yet have evidence that a large human community can run such a system for the full length of an interstellar voyage without supplies from Earth. Experiments such as Melissa can test components and connections, but a first ship would combine far more people, equipment, and biological change over far longer periods than those tests can reproduce. The durable image, then, is not a peaceful greenhouse. It is a greenhouse with a maintenance aisle running behind every bed, where someone can reach each valve before a crop is lost. If keeping the ecology alive becomes a permanent industrial job, how many people and machines must be devoted to maintaining the system that maintains everyone else? This part looks simpler at first than it really is. A ship launched later could carry better pumps, stronger filters, and sensors that fail less often. Yet its best advantage may sit inside a small freezer, seeds, microbes, and cell cultures chosen after many more years of closed-loop tests. That library wouldn't be a backup garden. Think of it as a box of spare parts for living chemistry. One crop strain might struggle under the ship's lights, while another needs less energy to grow. If the bacteria that process waste stop working, stored cultures might help rebuild the group. The hard choice is deciding which strains belong in the freezer. Each one must help the whole system without adding a new weakness. A later launch gains something that a faster engine can't provide: more years of biological tests. Researchers can watch plants and microbes through many closed cycles. They can change the light, heat, food supply, or number of people in a test. They can learn which groups recover after a fault, and which seem stable only while conditions stay mild. One good result may hide slow changes caused by growth, selection, harmful microbes, or constant human care. More time on Earth still won't solve everything. A ship would face conditions that no ground test could copy in full. The crew would change, and stored organisms would age. Microbes would keep evolving. Crops bred to give steady food might lose traits that become helpful after a new disease appears or a machine breaks. Even a large library couldn't hold an answer to every future problem. So the later ship must preserve variety without becoming a warehouse. It needs enough plant and microbial diversity to recover from trouble, while keeping each sample alive, separate, correctly labeled, and safe from the failure that harmed the working system. The freezer needs power, cooling, records, and spare parts of its own. Each vial needs a clear history, so the crew knows what it contains and when to use it. The safeguard becomes one more system that can fail. Closed-loop research can show how certain organisms act under set conditions. It can't yet tell us which collection would last through a whole interstellar trip. No experiment has followed a human ecosystem for that long, or exposed it to every failure it might meet. A later launch allows more tests, more generations of crops, and better choices. But it doesn't bring certainty. If the crew can carry only a fraction of Earth's biological options, who decides which forms of life are too important to leave behind? A dosimeter can make the radiation problem seem manageable because it records how much radiation reaches the crew. The number climbs slowly, day after day, even when no alarm sounds and nothing appears to be wrong. That steady rise comes largely from galactic cosmic rays, fast particles that come from beyond the solar system. Some carry enough energy to pass through a spacecraft wall and strike atoms inside it. Those collisions can produce showers of secondary particles, so adding more material doesn't always reduce the exposure in a simple way. The wall itself can become part of the event. NASA treats this background exposure as a serious limit for crews traveling beyond Earth's magnetic protection. Yet the evidence comes from missions lasting months, studies of exposed populations on Earth, animal experiments, and models of how particles move through tissue. None of those sources gives us a direct record of people living in deep space for decades. The missing years are exactly where the first ship would have to operate. That gap changes the design decision. The first ship can't merely include a storm shelter for the occasional burst from the sun. It needs living and working areas that reduce exposure every day, perhaps by placing water, food, fuel, and other supplies around the rooms where people spend the most time. A water tank then serves two jobs, keeping the crew alive and placing mass between them and some incoming particles. Even that design has limits. Cosmic rays arrive from many directions, and the most energetic ones are difficult to stop without an impractical amount of shielding. Magnetic or electric defenses have been proposed, but they would require large, dependable systems that haven't yet protected a crew on an interstellar voyage. The ship must therefore manage a hazard it may never be able to remove. And the burden isn't confined to a future cancer diagnosis. Radiation can damage the lens of the eye, blood-forming tissue, the nervous system, and reproductive cells. A small injury repeated across years may affect who can work, who can have children, and whether later generations inherit a healthy population. Our current evidence can identify those risks, but it can't tell us exactly how a mixed crew of different ages and bodies would fare over an entire lifetime in deep space. Waiting would improve particle measurements, shielding materials, and models of the body. Launching sooner would mean accepting wider uncertainty in nearly every health forecast. So how much protection must the first ship prove before its crew is being carried, rather than tested? At first, shielding seems like a simple purchase. Put enough material between the crew and space, and the particles lose their force before reaching anyone. But every protective layer has mass, and mass is one of the most expensive things a ship can carry. A useful object to keep in mind is a wall made of water. Water contains plenty of hydrogen, which helps slow some charged particles while producing fewer troublesome fragments than a dense metal wall might. A ship already needs water for drinking, washing, food production, and cooling, so its tanks could be arranged around living areas instead of sitting in one large reservoir. The crew would live inside part of its own supply. That sounds efficient until you follow the design through. Water gets consumed, cleaned, moved, and stored. A tank that protects a sleeping cabin today may offer less protection if its contents are needed elsewhere tomorrow. Pipes, doors, windows, maintenance spaces, and docking ports also interrupt the shield. Radiation doesn't care that a gap was convenient for the engineer. The same problem follows other materials. NASA and other space agencies test hydrogen-rich plastics and layered barriers because simply adding heavy metal can cause energetic particles to strike atomic nuclei and break into a spray of secondary radiation. The first impact is weakened, yet the collision may create new particles that continue into the ship. Protection, therefore, depends on the materials, thickness, placement and shape together, followed by tests of what comes through. And each choice spreads into the rest of the vessel. More shielding calls for more propulsion or a slower trip. Larger tanks need stronger supports. Stronger supports add more mass. If the ship spins to provide artificial gravity, that mass must be carried in a rotating structure that can survive years of stress and still be repaired by people far from a shipyard. There may be no single shield wrapped evenly around the whole craft. Designers could protect a smaller storm shelter more heavily, place supplies around sleeping quarters, and accept lower protection in spaces used briefly. That would reduce the launch burden, but it would also turn radiation exposure into part of the daily schedule. Where you eat, sleep, exercise, or repair a pump would affect the dose your body receives. No experiment has yet proved one complete shielding design across the full life of a generation ship. Materials can be tested, particle transport can be modeled, and shorter missions can provide biological evidence. But those pieces don't close every gap across decades of wear, changing stores, repairs, and crew movement. So before the first ship can justify launch, how much mass must it spend protecting everyone, and how much risk can it safely leave in the walls? This part of the problem looks simpler at first than it really is. A ship can leave Earth with a medical bay, trained doctors and shelves of drugs picked for the crew on launch day. But the radiation threat will keep changing while medicine on Earth moves ahead without them. The object to remember is a sealed medicine cabinet. On Earth, that cabinet depends on chemical plants, cold trucks, safety tests, spare parts, new research, and people who can make another batch. A deep space crew gets the cabinet, but not the system behind it. Far from Earth, each missing tablet or broken scanner becomes something the crew must make or repair aboard the ship. Radiation presses on both sides of the problem. NASA says exposure beyond Earth's magnetic field can harm DNA, raise the risk of cancer later in life, and affect the brain, heart, and central nervous system. That view comes from astronaut records, lab tests, and computer models. It cannot tell us exactly what several generations would face in deep space. The doctors would share that exposure, as would the drugs, electronics, living cells, and small biological factories used in treatment. A drug may leave Earth with a tested shelf life, but that test may not cover years of deep space radiation. NASA tests on the International Space Station have found that some stored medicines lose strength. The station, though, still gets some protection from Earth's magnetic field, and crews can receive fresh supplies. A generation ship would have neither advantage. It would face much longer exposure and illnesses that no launch team could fully predict. So the ship can't just carry enough medicine for a known list of diseases. The crew must be able to test whether drugs still work, make some treatments again, sterilize tools, repair scanners, and change its care as new evidence appears aboard the ship. It may need to make active drug ingredients from basic supplies, grow medical proteins in living cells, and check each batch without help from an outside lab. Researchers have tested parts of such a system. No one has proved a full medical service that could remain cut off for generations under deep space radiation. The human result is mildly awkward. A cure on Earth 50 years after launch might be cheap and common, yet out of reach, while the ship relies on an aging machine made by a company that vanished decades ago. Its hospital would have to serve as a clinic, factory, and research center, with the staff living inside the same long experiment as their patients. So what medical ability must the ship be able to rebuild before departure can be justified? A grain of dust seems like a small engineering problem until the ship meets it at interstellar speed. On Earth, the same grain might settle on a window. In deep space, it arrives as a tiny projectile and the faster the ship travels, the more damage that grain can do. You can feel the basic idea by dropping a pebble into sand, then throwing one hard. The pebble hasn't changed, but the faster impact drives deeper and throws more sand aside. A starship faces the same relationship on a far harsher scale. In basic mechanics, the energy carried by a moving object rises with the square of its speed. Double the speed, and the collision brings 4 times the kinetic energy. That follows from the standard kinetic energy equation, rather than any single proposal for a starship. Cruise speed, therefore, becomes a shielding decision. Each increase changes how much material the forward shield may need, how often damaged layers must be replaced, and how much spare shielding must leave Earth with the crew. More shield mass then requires more energy during acceleration. It may also demand a larger structure to hold the protection in place. The defense against dust becomes part of the propulsion burden before the engines even start. One design could place a thick sacrificial shield at the bow, built to absorb impacts while slowly losing material. Another could send thin clouds of particles ahead of the ship, so larger grains strike those first. Radar or optical systems might find some larger objects early enough for a small course change. Yet none of these methods clears away every tiny grain, and none has been proved during a crewed interstellar voyage, because no one has attempted one. The image to keep is a ship traveling behind its own battered front door. Every grain reaches that door first. Across decades, its surface becomes scarred, thinner, and harder to judge, while the crew lives far behind it without a repair yard or a replacement waiting nearby. Engineers can fire high-speed particles into candidate shield materials and measure the damage. Those experiments are valuable, but each test covers chosen particles, materials, and impact speeds. It cannot recreate every encounter waiting across several light years, or remove uncertainty about the dust lying along one exact route. So a launch plan can't simply select the highest cruise speed an engine can reach. It must select a speed the shield can survive, with enough protection for a dust environment that has not been measured grain by grain along the whole path. A faster crossing may reduce the years spent in transit, yet it also makes each unseen speck hit harder and adds mass that must be accelerated. How much speed would we surrender so that battered front door still holds near the voyage's end? This part of the problem looks simpler at first than it really is. A probe can put its shield at the front, tuck its electronics behind it, and accept damage that would be unthinkable on a ship carrying people. If one sensor fails, another may still work. If the outer skin becomes scarred, nobody inside has to breathe the air behind it. A habitat hull has a different job. It must remain a pressure vessel, a home, and a repairable machine for the full crossing. The wall around the crew cannot merely stop a grain. It has to keep holding air after the strike, prevent cracks from spreading, and protect pipes, cables, water stores, and living space packed close behind it. The memorable image is less like an armored arrow and more like a house traveling behind a battered front porch. That changes the design decision. On a small probe, engineers may place a thick sacrificial layer in the direction of flight and let that layer erode. The useful parts can sit in its shadow. A crewed ship may also lead with replaceable shielding, but the protected shape is much larger, and people need spaces that cannot all hide inside one narrow line. Every extra square foot of forward-facing area asks for more shield, while every extra pound of shield asks the propulsion system to push harder. There is another awkward difference. A probe does not need to walk outside and mend its own front edge. People might. Yet the safest place during flight is behind the very material that could need inspection, and damage may be too small to notice until it reaches a seal or weakens a later repair. Designers can add separate layers, gaps, sensors and spare panels, but each answer brings more joints and more mass. Protection becomes a system, not a slab. Ground tests can show how selected materials respond to selected impacts, and computer models can extend those results across cases that are difficult to fire in a laboratory. They cannot certify a crew habitat against every grain on a route whose dust has not been fully mapped. That source boundary is important. We know enough to compare shield ideas and reject fragile ones, but not enough to promise that a large human hull can cross untouched. So the first ship cannot borrow a probe's survival record and simply scale up the metal. It must decide how much damage is acceptable, which layers can fail without losing the cabin, and what the crew could repair far from help. If the habitat has to survive as both shield and home, what kind of hull can take repeated hits without becoming too heavy to launch? Speed can look like the cleanest setting on the ship's design screen. Raise the cruise speed, shorten the crossing, and spare the crew years of food, maintenance, and confinement. But the faster ship does not merely arrive sooner, it meets every grain of dust with more energy, and it must carry the material needed to absorb that energy. A bicycle gives you the small, familiar version. A flying insect at walking pace is nothing. Meet it while riding downhill, and the same insect can sting your cheek. The insect has not changed. Your speed has changed what the collision does. For a starship, the object might be a grain smaller than sand, yet the closing speed turns it into a sharp pulse of heat and pressure against the forward shield. That puts a physical object at the center of the speed decision, the shield at the ship's nose. It may need several layers, with space between them, so the first impact breaks a grain apart, and later layers catch the spreading debris. That basic approach has long been used against small impacts in space, including designs based on the Whipple shield developed for spacecraft protection. But a method that works in Earth orbit does not by itself settle the demands of a much faster interstellar crossing. The impact speeds, travel time, exposed area, and repair distance are different. More protection means more mass. More mass demands more propulsion, which needs more energy and may require still more structure. Even a modest increase can move weight from payload into protection. If designers then raise the speed to shorten the trip, the protection problem grows again. Speed has been purchased twice, first through the engine and then through the hull that must survive what the engine makes possible. There may be ways to shift part of that burden. A ship could send material ahead, use magnetic or electric fields against charged particles, or accept a slower cruise through regions thought to contain more dust. None of those choices removes the source limit. We do not yet have a complete grain-by-grain map of an interstellar route, and proposed field systems do not offer the same answer for every neutral particle. The final design would still rest on models, tests, and a stated level of acceptable risk. So the launch decision cannot begin with the fastest speed an engine might reach. It has to begin with a speed the whole ship can afford, including the shield, the fuel, the repairs, and the uncertainty ahead. How slowly must the first ship travel before its protection becomes something we can justify? This part looks simpler at first, because Earth keeps getting better at solving technical problems. A ship launched later may have stronger materials, better computers, and more reliable ways to recycle air and water. Waiting can improve the design. Yet waiting also creates a decision nobody can settle with a laboratory test. How much future progress should be expected before the ship leaves? Think of a locked tool cabinet aboard the ship. Every wrench, circuit board, sensor, and spare pump must either be carried from Earth or made during the voyage. Engineers on Earth can change a factory whenever a better method appears. The crew cannot replace its whole industrial base so easily. Its tools must be able to repair machines whose failures may not have been foreseen when the cabinet was packed. That makes progress on Earth a mixed gift. Better manufacturing can move launch closer by reducing mass or making parts last longer. Better astronomy can sharpen the destination. Improved medicine may lower risks that once seemed unacceptable, but each improvement can also reveal that an earlier design was less ready than its builders believed. A new sensor can expose a hazard that the old sensor simply missed. There is another complication. Progress does not arrive at a steady pace, and it does not spread evenly across every system the ship needs. Computers may improve while closed-loop farming remains difficult. Materials may become lighter while radiation protection still demands mass. A breakthrough in one area can even create fresh burdens elsewhere, because a more capable machine may require new power supplies, new cooling, and new kinds of repair. We have strong evidence that engineering changes over time. The machines around you make that clear enough. What we do not have is a dependable schedule for inventions that have not happened. No study can tell a mission planner exactly when a missing technology will appear, how well it will work, or whether it will survive years of testing. Forecasts can describe possible paths. They cannot turn those paths into dates. So the first ship faces an awkward choice. Launch too soon, and its crew may spend the voyage with systems that Earth soon learns to replace. Wait too long, and each new improvement becomes another reason to delay, because the next design may always look safer from the ground. The ship can become permanently almost ready. A justified launch would need more than confidence in current hardware. It would need a clear rule for what must be solved before departure, what the crew must be able to solve alone, and which later discoveries on Earth could still reach the ship as information. Once those limits are set, how do we decide when waiting has stopped protecting the mission and started preventing it? A radio message seems almost weightless compared with a starship. It needs no fuel tank, no food, and no sleeping crew. Yet it may carry something the crew badly needs, a better way to use the machines already aboard. That makes Light a strange kind of supply ship. Earth could send new software, revised medical guidance, improved crop schedules, or instructions for diagnosing a fault that nobody understood when the vessel left. If a telescope near home found a hidden hazard near the destination, that warning could follow as well. The crew wouldn't be cut off from human knowledge just because no physical cargo could catch them. But information can only change what the ship was built to accept. You can send a repair manual to someone with the right tools. You can't send the missing wrench inside the manual. A new reactor design is little help if it depends on materials, factory equipment, or parts that do not exist aboard the ship. Even software may be useless when old sensors cannot collect the needed data, or when a computer lacks enough memory to run it. So the launch decision reaches backward into the design. The ship needs machines that can be inspected, altered, and used in ways their makers did not predict. It needs spare capacity in its computers and power systems, plus workshops able to turn instructions into objects. That extra capacity has a cost. Every unused connector, adaptable tool, and reserve of computing power adds mass, complexity, or another possible failure. Flexibility is not free. There is also the delay. A message travels at the speed of light, which is as fast as any known signal can go, but the ship is leaving its source behind. Replies take longer as the distance grows. A crew may describe a failing pump, then continue living with it while the report crosses space, and Earth's answer makes the same trip back. Advice can arrive after the crew has already made the decision. Earthside progress therefore helps most when it can be compressed into knowledge the ship can use without waiting for a conversation. The durable image is not a parcel racing through space. It is a thin beam reaching a distant workshop, carrying plans but no hands, no metal, and no guarantee that the old machine can become the new one. We can't know which discoveries would appear during a voyage, or which failures would make them urgent. We can only decide how much room to leave for change. So what must the first ship carry before Light can carry the rest? This part looks simpler at first than it really is. If Earth develops a better system after the ship leaves, you send the plans, the crew builds it, and everyone benefits. But the object waiting at the other end of that message may be a sealed life support unit whose pipes run through 3 decks. Replacing it would mean stopping a machine that people need every minute they are alive. Now the crew has more than an engineering problem. They have to decide who may authorize the risk. The new design might use less power or need fewer repairs, yet installing it could interrupt the air supply, consume scarce material, and occupy the ship's best technicians for months. The people who designed the replacement are far away. The people who would bear the consequences are on board. That distance changes the meaning of obsolescence. On Earth, an old machine can be retired because a factory has made another one. A service team can arrive, and a failed installation doesn't threaten an entire community. A generation ship has no spare city waiting nearby. Its outdated equipment may still be the only equipment with a long record of keeping people alive. So the choice won't belong to engineers alone. A council may favor the upgrade because it protects children who will inherit the ship. The maintenance crew may oppose it because they know where the hidden cracks are. Families living beside the work area may face months of noise, restricted water, or evacuation from their rooms. Even a clearly better design can divide people when its benefits arrive later and its dangers arrive now. The first ship must therefore carry a way to govern change, not just the tools to perform it. That could mean rules for testing a new part in isolation, preserving the old system until the replacement proves itself, and deciding what level of risk requires consent from the wider population. Those rules would need trust. We don't know which form of government could hold its authority across many generations. We also can't claim that any starting charter would survive every emergency unchanged. The durable image is a worn valve on a council table. Everyone agrees that a newer valve exists. What they dispute is whether this one should be removed tonight, who gets to decide, and who answers if the new one fails. Progress on Earth has reached the ship, but it has arrived as a political choice. If every upgrade can redistribute danger, work, and power, how does a crew keep necessary caution from becoming a permanent refusal to change? This part looks simpler at first than it really is. A ship reaches its destination, the engines slow, and the people aboard begin building a home. Yet arrival does not erase the rules made during the voyage. It gives those rules a new problem. The people who must live with them are no longer the same group that agreed to leave. Consider one sealed document carried in the ship's archive, the landing charter. It says who may choose the first settlement site, how water and power will be shared, and what happens if two groups claim the same ground. During departure, those terms may have seemed practical. At arrival, they decide who gets safety, access, and a voice. Some of the adults opening that document may have been born aboard the ship. Their children certainly had no chance to approve its rules. They inherited the mission along with the air system, the engines, and every promise made before their birth. A charter can pass from one generation to another. Consent cannot be stored so easily. Earth offers legal traditions, constitutions, and treaty systems that could inform such a charter. But those examples come from people who can often challenge authority through other institutions, leave one jurisdiction for another, or appeal to communities beyond a single settlement. The first arrivals may have none of those exits. If the council controls the air, shelter, food, and transport, losing a political dispute could also mean losing the systems that keep you alive. That makes the landing site more than a patch of ground. A decision about where to place the first reactor or water plant can shape power for decades, because whoever controls the shared equipment may also control who can move away. Even a fair rule on paper can become coercive when there is nowhere else to go. The charter would therefore need more than a method for choosing leaders. It would need protected access to life support during political disputes, a way to remove officials, and a process that later generations can change without asking permission from the very people whose power is being challenged. None of that is easy inside one sealed settlement. We do not have evidence that one form of government can remain legitimate through a voyage and then through settlement under conditions no human society has faced. We can say only what the burden would be. Before launch, the mission needs a credible way for later generations to revise inherited rules without letting a small group seize the life support system during every dispute. So keep the landing charter in mind, opened on a table by people who never signed it. The ship has completed its planned voyage, but its authority has not earned permanent ownership of their future. Once the doors open and a settlement begins, who has the right to write the next version? This part looks simpler at first because the first settlers took the greatest risks. They crossed the distance, kept the machines running, and built the first sealed rooms. It may seem fair that they should decide who enters, where later arrivals live, and how supplies are shared. Yet all that power could rest in something as small as an airlock access code. At first, the code is a safety tool. Someone must control the door, check the pressure, and stop one bad entry from risking every life inside. But control of the door can slowly become control of who belongs, A family arriving later may need the settlement for air, power, medicine and shelter, yet have no vote over access to those things. The pioneer becomes the gatekeeper. The newcomer becomes a plaintiff, asking for rights from people who already hold the means to stay alive. No settlement beyond Earth has tested this problem, so we can't say one legal design will solve it. Laws on Earth grew in places where people can often leave, appeal to another court, or survive outside the building at the center of a dispute. A remote settlement removes much of that protection. If one authority controls every safe room, being refused entry isn't like being turned away from a club. It may leave you with nowhere to breathe. The landing charter must account for that. It can respect the work and risk of the first crew without making first arrival a permanent political rank. It can also keep urgent safety choices apart from choices about membership. The person guarding an airlock may need to close it during a pressure failure. That same person shouldn't be able to use the code to silence a rival, punish a family, or win a fight over voting rights. Appeals would need clear deadlines, review by people outside the dispute, and a way to work when help from Earth takes years or never comes. They would need real force as well. A ruling has little value if the Council can ignore it because it controls the doors, power lines, food stores, and repair crews. The hard part is deciding who can provide a fair review when every judge, technician, and council member relies on the same life support system. We have ways to divide public power on Earth. We don't know whether they will stay fair in a place where one broken pump can shrink everyone's choices. The first ship moves closer to a justified launch only if its rules protect those who arrive after the Founders, including people the Founders may dislike. If access to air is also access to society, who gets to hold the code? This part seems simpler at first. Put a constitution in the ship's archive, require every officer to follow it, and carry the same rules all the way to the destination. But a document written before launch can only govern people who agreed to leave Earth. It cannot ask consent from the children born during the voyage, or from the adults those children become. The durable image is a sealed copy behind glass. It may survive every engine burn and every change of command, yet arrive with less authority than it had at departure. The settlers opening the case could be living under conditions its authors never faced. They may have found unsafe soil, scarce water, damaged equipment, or a better landing site than the one named in the plan. If the rules cannot change, the dead govern the living. If they can change too easily, whoever controls the first settlement can rewrite everyone else's rights. So the Constitution needs more than a list of freedoms. It needs a lawful way to revise itself after arrival, with limits that a frightened majority cannot sweep aside. That could mean protecting access to hearings, records, medical care, communication, and the basic systems required to stay alive. The exact design remains unsettled. Earth has many constitutional models, but none has been tested in a settlement where leaving may be physically impossible and government operates the machines that keep every resident breathing. Arrival adds another burden, deciding who belongs. A person awakened from suspended travel, a child born aboard the ship, and someone transferred from a later vessel should not depend on a founder's invitation to become a full member of society. Citizenship tied to ownership, technical rank, or family descent would allow the first crew to harden into a permanent upper class. Even a fair founding group could create that result by accident, simply by passing scarce land and key jobs to its own children. A launch becomes easier to justify if membership follows the person rather than the founder's favor. Rights would begin at birth or arrival, not after years of service. New residents would have a path into public decisions, and no council could label them temporary guests forever. Still, this does not tell us how quickly newcomers should gain a vote, how settlements should divide shared resources, or whether one habitat may separate from another without endangering both. The sealed document, then, is not the Constitution. The Constitution is the process that lets people reopen the case without letting the strongest person replace its contents. Before the ship leaves, can its founders design a government that accepts their descendants may lawfully choose something else? This part of the problem looks simpler at first than it really is. Once a ship has working engines, stable life support, and a government its passengers can change, departure can seem like a date on a calendar, yet the most important object may be a much smaller one, the launch key, held beside a checklist that no generation has ever completed before. Turning that key depends on which future the builders fear most. If they expect steady progress, waiting may look sensible. A later ship could be faster, safer, and less costly to maintain, leave too soon, and the first travelers may watch a newer craft pass them before they reach another star. That is possible, but no historical record tells us how quickly technology will improve across the centuries required for such a project. That uncertainty belongs inside the launch decision. Stagnation changes the decision. A society may remain capable of building the ship while losing the public trust, spare resources or political patience needed to launch it. The plans can stay in storage, the factories can keep running, yet each committee asks for one more test, because delay feels reversible and departure does not. The launch key then becomes a way of measuring confidence, not engineering alone. Collapse pushes the choice in the other direction, though the evidence cannot tell us when or whether a global collapse will happen. A ship built as insurance must leave before the danger arrives, but predicting danger too strongly can turn the mission into a panic project. Its passengers may be chosen badly, its systems rushed, and its purpose narrowed to saving whoever already holds power. Fear can move a launch closer while making the voyage less defensible. Then there is seeding, sending life, stored embryos, or automated biological material without sending a living human community. Such a craft could be smaller than a generation ship, but the smaller payload does not settle the moral problem. It moves the burden into machinery that must cross interstellar space, reach a suitable world, and begin a living system without human repair. We have no completed case that shows this chain can work beyond Earth. So the forecast is not a single curve pointing toward departure. It is a choice among waiting for better tools, leaving before capacity fades, and sending something less than a society because a full ship remains out of reach. Each path changes what counts as success, and none comes with a tested timetable. When the launch key is finally placed on the table, what evidence would be strong enough to justify turning it? This part looks simpler at first because a departure forecast arrives as a date on a chart. Someone draws a line through rising engine performance, extends it toward the point where a ship becomes possible, and marks a launch window. The line feels firm, the date does too, yet the chart can only follow the parts of the ship that have already become measurable. Think of a clipboard beside a half-built machine. The engine team may know how much thrust its design should produce, while the life support team knows how long its filters have lasted in a test chamber. Those results are real, but neither one tells you when the whole ship will be ready. Each system depends on others, and the slowest problem may remain hidden until two finished parts are connected. That is where forecast error grows. A planner can estimate known work, add time for expected failures, and still miss the fault that nobody has learned to name. Perhaps a seal ages differently under radiation. Perhaps crops survive alone but fail when their water, microbes, and waste must cycle together. The schedule does not slip because every estimate was foolish. It slips because the object being forecast has never existed as a complete object. There is a human wrinkle here as well. Teams report progress through the pieces they can count. Tests passed, mass removed, power saved. A launch decision has to judge the spaces between those pieces. A long list of successful trials can create confidence even when no trial has carried the full burden of isolation, repair, and time. The clipboard gets heavier, but the ship may not be much closer to leaving. This does not make planning pointless. It changes what a responsible forecast can claim. A date based on component progress is evidence that certain tools are improving. It is not evidence that an interstellar system will be ready on that date. Until integrated tests expose how the parts behave together, any launch year remains conditional, tied to assumptions that should stay visible beside it. A test program can reduce that gap only by joining systems early, then running them long enough for slow dependencies to appear. Even then, Earth cannot reproduce the entire trip. Testing can uncover failures and narrow uncertainty, but it cannot prove that every slow interaction has been found. The first ship, therefore, approaches its launch key through a series of forecasts that become better without becoming certain. So, when a schedule finally says the ship is ready, how much of that confidence comes from the machine, and how much comes from the date we chose to believe? This part looks simpler at first than it really is. Somewhere near the end of planning, someone must place a departure date beside the ship's name and treat both as real. The name may be painted across the hull, but the date does more work. It tells the farms when their first harvest must be dependable, tells the crew when training stops being practice, and tells every supplier when the last replacement part has to be aboard. A forecast has become a commitment. That change is easy to miss because the date still looks like a line in a schedule. Yet moving it by a few months can alter who flies, which stored materials age before launch, how much testing remains possible, and whether a system leaves Earth with a known weakness. The calendar isn't sitting outside the machine. It has become one of its parts. You can see the burden in a simple object, the sealed cargo door. Before it closes, engineers can replace a pump, inspect a cable, or load another set of filters. After it closes, every change costs time, and some changes disturb systems that have already passed their tests. At some agreed point, the ship must stop improving and become the ship that will actually leave. Departure forecasts, therefore, depend on more than estimates of technical progress. They depend on decisions about how much evidence counts as enough, which remaining faults can be managed in flight, and which unknowns are serious enough to keep the door open. Those choices cannot be settled by the schedule itself. There is no measured record of completed voyages like this one. We have long-duration machines, closed system experiments, isolated crews and components tested under harsh conditions, but none of those sources reproduces the whole mission across its full span. They can support parts of a forecast. They cannot supply a verified departure rule for the complete ship. That boundary changes the meaning of readiness. A ship may satisfy every test its builders knew how to design, while still carrying interactions that no test revealed. Waiting longer can expose more of them, though time also ages hardware, changes crews, and invites redesigns that require fresh testing. Delay is not automatically caution. Launch is not automatically courage. So the mission's real name is written less like a title and more like a signature beneath a decision. This is the configuration we accept. These are the limits we understand, and these are the uncertainties people will carry beyond repair from Earth. The durable image is still that cargo door, closed and latched, not because the work is finished, but because someone has decided that further work on Earth would no longer justify keeping it open. The forecast becomes a departure only then. At the start, a valve needed repair. Someone opened a panel, traced the fault, replaced a worn part, and returned the air system to service. It looked like a small engineering job, the kind of maintenance any long voyage would require. But on a ship built for descendants rather than passengers, that repair was also a political act. The person holding the tool had learned the right procedure, trusted the records left behind, and accepted that keeping the ship alive was more important than changing its purpose. That is the wager beneath the machinery. A generation ship can't be judged only by whether its engines run or its hull survives. It has to carry a reason for continuing, and that reason must remain strong enough to guide people who never agreed to leave Earth, will never see Earth, and may not live to see the destination. The debt begins with speed. Leave too soon with a slow drive, and a later ship may pass you. Add more power, and the ship needs more fuel, shielding, cooling, and repair capacity. Add that mass, and propulsion becomes harder again. Then biology joins the account. People need food, gravity, or some substitute for it, protection from radiation, medical care, and enough genetic and social depth to keep a closed population healthy across many generations. Politics inherits every unpaid balance. Someone must decide who works, who receives scarce treatment, whether the mission can change, and what happens when the people alive no longer believe the promise made by the dead. The air system may be closed, but the argument over its purpose never is. Even a sound repair procedure depends on people accepting who may rewrite it, who may refuse it, and who carries the cost when a decision fails. None of this proves that the first ship would be foolish. It may be answering a harsher problem than getting there quickly. If technological progress has slowed, leaving early could make sense. If Earth faces collapse, waiting for a better engine may be the greater risk. A mission might also aim to seed life beyond one world, or to build a mobile civilization whose value doesn't depend on arriving before anyone else. Those cases change the overtake calculation. Being passed is embarrassing only if first arrival was the main goal. A ship designed to preserve people, knowledge, and a working society could still succeed even if a faster vessel reaches the destination decades earlier. Its success would be measured by continuity, whether children inherit a habitable world, whether authority can change without breaking it, and whether the mission remains theirs to accept. We have stronger public evidence for the direction of these trade-offs than for the exact date when they tip. Propulsion may advance quickly or stall. Biological repair may become powerful enough to reduce several risks, though we don't know how far it can go. A government designed on Earth may last for centuries, or fail under pressures its designers couldn't test. No current forecast can combine those unknowns with enough confidence to name a safe launch year. That leaves one forecast no instrument can yet settle. When has progress slowed enough that leaving now is safer than waiting? Go too early and the ship carries avoidable debt. Wait too long and the chance to leave may close. So the valve repair returns us to the choice beneath the voyage. The first ship stays rational only if its people value continuity more than victory, and build a society capable of making the same choice after its founders are gone. The destination is important. Remaining a civilization on the way there is the harder requirement.